Before we get started or get into our presentation today, I do have just a few housekeeping slides to go over. First of all, hopefully you should be hearing me speak now, but if you have any difficulties throughout the webinar today, I just wanted to mention that there are two different ways to connect to the audio. One is through your computer audio, and then the second option is through your phone. So for some instance, if you have any issues with that throughout today, feel free to switch to the other one. And due to the large number of attendees that we do have on today's presentation, we have gone ahead and muted everybody's phone lines, but don't worry, there is still a way that you can interact with our speaker today. And in terms of interacting with our presenter, you can ask your questions via the questions panel at any time throughout the webinar. And at the end of the presentation, we do have some time set aside to answer questions. So feel free to go ahead and ask any questions that come to mind, and we will try to get through as many of those as time allows. And if you haven't already seen, today's presentation is one of several that we are conducting in a 3-week live series. You can check out the complete series on our website at www.veoliawatertech.com. You can check out the whole series that we have, as well as go ahead and register for any of those that are upcoming. And in addition to the live webinars that we have also gone back through our arsenal and put together a collection of all the on-demand webinars that we've conducted throughout the last couple of years. You can access those on-demand webinars also at www.veoliawatertech.com. And just one other quick housekeeping note, we are offering PDF participation certificates. Those will be made available to you at the conclusion of the webinar. You should receive those in approximately 24 hours or so after the webinar is completed today. And one more thing is we do like to we're asking for your feedback. At the conclusion of today's webinar, you'll receive a quick survey requesting your feedback. Should only take about 20 to 30 seconds of your time. And for those of you who do complete the survey, you'll be entered into a drawing for a chance to win a $25 gift card. So we do appreciate that if you do take your time to do so. Okay, just one more quick slide before I introduce today's speaker. Veolia Water Technologies. We are a leading company within water treatment. We focus our efforts in 3 key main areas. Technologies, we offer advanced and robust water treatment technologies. We have a large portfolio of over 350 proprietary technologies that we are able to offer our clients. In addition to our technologies, we are able to pair those technologies in terms of developing projects for our customers, and also to put multiple technologies together to meet the required treatment specifications of our clients' needs. And then lastly, we have a very thorough service offering that we can provide, whether it's during projects or after. Okay, so now I'd like to introduce our speaker for today's webinar. Miriam de la Durante Noel is a process engineer at Veolia Water Technologies, Canada. She graduated from Polytechnique de Montreal with a degree in geological engineering. Her previous roles at Veolia have included piloting, R&D development, and laboratory studies. As a process engineer, she has the opportunity to use her competences and field experience in water treatment by designing water treatment chains for the heavy industry, aiming to reach ever stricter environmental compliance. So now I would like to turn it over to Miriam. Are you with us, Miriam?
Yeah, sure. Thank you, Jill. So good afternoon or good morning, everyone. Today we will talk about reducing toxicity of a Canadian gold mine. So what we will go through today is first, this is a case study. So first we will explore the issue the mine has regarding toxicity. Second, what were the options to reduce the toxicity? And third, it's how do we implement the solution to the project in question? So through lab work, piloting, and building a full-scale application. And then we'll present some results from the full-scale operation, which is ongoing for the last 36 months. And we'll conclude with the main conclusions of the case study presented today. So the issues. This is a mine operated by Goldcorp and now part of Newmont. It's a large gold mine in northern Quebec. There was a water treatment plant built by Veolia in 2013. This water treatment plant aims the metal removal. It's a two-stage metal removal, first for heavy metal removal, second for arsenic removal. After the startup of this water treatment plant, the mill was started at the mine and the effluent was toxic. So the mine was asked by the regulator to stop the toxicity or to stop operation altogether. So at that point, people from Goldcorp has contacted Veolia to ask some advice about reducing the toxicity they experience at the mine. So what is the law that the mine has to respect? Is there's two levels of regulation, federal, provincial, or federal, state, depending of where we are. In most regulations, you have discharge criteria about pH, total suspended solids turbidity, metals, and toxicity or acute lethality. So your effluent has to be non-toxic or non-acutely lethal. In the case of the mine we are currently exploring today, it's toxicity to rainbow trouts and daphnes, which are the Canadian regulation. So before finding toxicity issues with the mine, you need some context to understand what is the mine experiencing. So the mine is extracting gold using a cyanide process. As many of you know, a cyanide process creates a very toxic water, especially for dogs or mammals. So the gold mine effluent goes to a detoxification process. In the case of the mine we are looking at today, it's an Inco SO2 air process. So after detoxification, the water is considered non-toxic to mammal. Dogs sitting in a pond won't die, but for fishes and invertebrates, this is not the same thing. Fishes and invertebrates doesn't like effluent from detox system. So the effluent was characterized by presence of cyanides, residual, cyanate, copper, thiocyanate, and ammonia. The copper was already addressed with the water treatment plant on site for metal removal. So what could be a cause of toxicity at the mine was cyanide species and ammonia. So how to remove cyanide species and ammonia in order to reduce the toxicity in a mine effluent? First, there are some hypotheses that need to be posed before starting anything. The toxicity could be a combination of ammonia, cyanide, and or thiocyanate, depending on the concentration of each of these species. And we know that ammonia, cyanide, and thiocyanate are biodegradable under aerated conditions. So what we thought what could be a solution is a biological reactor, which should be able to completely remove the toxicity from these constituents with regular biodegradation in aerated conditions. What are the principles of biological treatment? I'll go quickly over that just to make sure everyone is on the same page. The biological treatment is based on oxidation when you're using an aerated process, or reduction with the anoxic process of a pollutant of interest using specialized bacteria. Each pollutant has a different bacteria that might be able to degrade the pollutant. The main pros of biological treatment is it's the low maintenance process. and it requires little chemicals. It just requires chemicals for biological growth, but there's no need of coagulants or any dangerous chemicals. What are the main cons of the biological treatments is if there is a toxic compound, it can disturb biological activities. It won't necessarily kill everything, but it will inhibit the biological activity, thus reducing the efficiency of the process. Second, bacteria requires nutrients to support activity. It's a living thing, so it needs nutrients. So you need to make sure these nutrients are in the water. Biological treatments are sensible to sudden variation of temperature and loading. We're not talking about gradual variation, such as when the snow is melting on site or anything like that. It's like a really sudden variation. There's a chemical spill. So this is sensible to these kinds of events. Startup of a biological treatment can be long because you have to grow your biomass. So this, depending of the kinetics of your bacteria, can be long. And seeding may need to be redone if there's a severe toxic shock event. There's a chemical spill, you may need to seed again your system because you may have lost part of your biomass. The technology we're mostly using in biological treatment is the MBBR. The main reasons for that selection is it's a fixed growth technology. It's more robust, it's more compact. It got a slight tolerance to isolated toxicity events. If there's a big spill, nothing biological will survive, but if it's a slight spill, it may be able to overcome the spill because the biomass is protected. Operation can be made at low temperature, can go as low as 1 degree C. It's self-regulated because the biomass is, the carriers where the biomass is growing is either mixed with a mechanical mixer or with aeration. The carriers are grinding themselves together and they're self-regulating the biomass. So that biomass will slough off and will go out of the system, and you don't need to do any maintenance on these. There's a high tolerance to hydraulic flow as long as the loading is similar. High tolerance for TSS in the effluent. TSS doesn't bother the biomass at all. And reactors can be installed in series. Several reactors can be installed to remove different pollutant in the same treatment chain. So now, biological treatment, what are the applications in cyanide removal, ammonia removal? First, cyanide, we want to remove them because they are highly toxic. Most of the removal is done by chemical oxidation, such as the INCO SO2 air. This produces cyanides. You can also remove cyanide using biological treatment. If you have any leak of cyanide to your biological treatment, the biological treatment would be able to take care of it to remove the cyanide from the final effluent. And product using biological treatment is ammonia. Cyanide needs to be removed because it's toxic to mainly the Daphnia amania or any Daphnes. It can also inhibit nitrification process, and this is a source of ammonia. So you're inhibiting nitrification, you're adding ammonia. Ammonia is toxic, so you want to remove cyanide also. Biological treatment is made by aeration. It's an aerobic biological treatment in neutral conditions, and the end product is ammonia. Cyanides, these are a byproduct by the contact of cyanide and a sulfide source such as pyrite. Why do we want to remove them? Once again, it can inhibit the nitrification system. It's a source of ammonia. And it could be toxic, but at high concentration. So you mainly want to remove them to make sure there's no inhibition to the nitrification. The particularities for biological treatment, it's an aerobic biological treatment, neutral conditions, and you're producing ammonia once again. So once you remove all your cyanide species, you have a lot of ammonia. Now you need to remove ammonia. Why? Because ammonia dissolves to unionized ammonia. which is toxic, acutely toxic to aquatic life, to both fishes and vertebrates. So you really need to make sure this unionized ammonia concentration is not high. You can control it slightly with pH, but most of the time at the ammonia concentration you have to remove your ammonia beforehand. So ammonia removal is based on an anaerobic biological treatment in neutral conditions. It creates final oxidation goes to nitrates, and oxidation of ammonia to nitrate creates acidity. So you'll need an alkali dosage to control the pH, because when you lower the pH, you're causing inhibition of your nitrification. And to go a little bit further, if you have some regulation on total nitrogen removal, like in some states and in some provinces in Canada, you have to remove nitrates. Nitrate is not toxic. It can cause eutrophisation of the lakes and rivers, but it's not toxic. But you can still remove them using anoxic treatment. Still in neutral pH, but this is a mixed reactor, no oxygen, and you need a carbon source to reduce nitrate to final nitrogen gas. So now, this is great, but it's not enough. For the case study, you know, toxicity is a complex issue, and it's hard to find the exact cause of your toxicity, and how to correctly control your process to completely remove the toxicity. It must be done by trial and error. Now, in the case study present here of the gold mine, some lab testing was completed. There was a setup of two MBBRs for removal of the cyanide species and the ammonia. And the startup was made at room temperature, and what was observed is you could remove cyanide, you can remove cyanate, you can remove thiocyanate. It took a fair amount of time by the time everything is seeded, because we didn't have the sources of bacteria, and we started from carriers with none, so it took some time for the biomass to construct itself. But there was the ammonia removal was incomplete, because for some reason there was a nitrite buildup in their reactors, and these nitrites was creating an inhibition to ammonia removal from nitrite to nitrate. So what was the hypothesis? Maybe there is some copper inhibition that prevents biological activities. There was a modification to the setup to make sure the copper was was low enough to make sure there's no inhibition at all from copper. After a couple months of operation, the nitrite were still fairly high, but most of the ammonia and cyanide species were removed. There was collection of the water sent for toxicity. Unfortunately, the water was found to be still toxic. However, if you look at the LC50 for both rainbow trouts and daphnes, the LC50 increases, meaning that the water is less toxic than it used to be. So it was on the right path. Then what could be the problem? Looking at the first two paths, the first reactor was degrading cyanide species with high efficiency, no problem. There was a high concentration of ammonia, but also a high concentration of nitrites and little nitrates. The second reactor was doing the rest of the job. So what was posed as an hypothesis? Maybe the first reactor is too efficient, and there's a problem between the two reactors. If you feed to the capacity of the cyanide degradation, there will be too much to remove for the nitrification reactor. And on the contrary, if you feed the reactor correctly, if you feed the treatment chain to accommodate the nitrification, your cyanide degradation will be less efficient. So the final task of the lab testing was to modify the reactor size to have a smaller reactor for cyanide degradation and a bigger for nitrification, which worked really good. Within a couple of weeks, the nitrate concentration was decreased. The water was non-toxic. So since it's a cold water application, the temperature was decreased in the lab from 25 to 4 degrees Celsius, which proved that biological activity decreases as expected. In low temperature, it still works, but it's slower. And the water remained non-toxic. So this is really good. But now, is this solution going to work in a full, well, is it going to work in a full-scale application? So what was done is we got piloting in Veolia, piloting units. A pilot was sent to the site to test directly from their middle removal effluent to see if the water could be non-toxic and if the biological treatment works well. Why did we do this piloting? Is because the water source is fluctuating over time and we want to make sure that the fluctuation won't affect the biological efficiency. The same setup was completed at the pilot scale then in the lab. We just added some denitrification step to see if we can do complete nitrogen removal, but it's pretty much the same setup. The result, as expected, there's a wide variation of the water quality going in the pilot. However, no matter the variation, thiocyanide degradation was very good, no matter temperature, and ammonia degradation was also nearly completed. What you can see here, the white foam, it's very interesting. There was some spill of soap or any maintenance product during operation of the plant, and the water goes to the biological treatment. It created toxic shock in the pilot. So during a short period of time, the bacterial activity was inhibited. We could see IDO in the water, meaning that there was no oxygen consumed by the biological, meaning the biomass was not doing its job for a short period of time. However, it started its activity fairly quickly after, when the toxic shock was gone. So this shows that the technology was very robust. Well, it was demonstrated that it was very robust, so it's good for a full-scale application. These kind of things are rarely shown in the lab scale, so it was a good thing to see them during piloting. So quick overview of the pilot results for 6 months operation. Cyanide species and ammonia were very low at the effluent, and most importantly, right here, there was no mortality for both fishes and daphnes during the whole period test. So now, once we proved that we managed to control the toxicity and to remove the toxicity from the mine effluent, in collaboration with the clients, we went to the building of the full-scale application. The basic design of this full-scale application is first establish the load of nitrogen to treat. You receive cyanide, ammonia, and you need to determine what is the final nitrogen loading that the system will see. So the challenge is the mill is running as a loop, and you don't know exactly how much nitrogen needs to be removed. Denitrification is not required in this case because there's no discharge criteria for total nitrogen. So since it's not toxic, we just get to cyanide removal and ammonia removal. Design temperature was fixed at 8 degrees Celsius. So there was addition of a water heater to make sure during winter that we can operate. And there's a high chloride concentration. So material selection and corrosion protection were very important in that application to make sure to protect every equipment from corrosion. These are a couple of layouts to show that this is the existing plant, the auxiliary equipment for the MBBR, and the MBBR installed. These are projection if they want to add denitrification later on. This is the inside, just to show you the scale of MBBR. This is pumping for MBBR, heat exchangers. This is when they built the system. This system was built during winter. It was a winter construction, so a lot of challenges. But this is when they installed the base ring, and then they just erected the field erected tanks. These are the tanks once they finished to construct the shell. It's operated in winter, it's outside, so it's installation of insulation, and this is the final look of the MBBR reactors as seen today on site. So now what you are most interested in is the result of the operation of this full-scale application. This is the first 34 months of operation at a glance. Don't worry, we'll get through them once at a time. First, loading. So now I will ask you to concentrate on the little green triangles. You can see that the treated load is increasing over time since the startup. Well, it increased for a period of time at least, as the operators increase the amount of water going in the system to make sure that they start up properly and not just send the whole loading at the same time. So the peak load is 130% of the design load, which is very good because we treat more than what we expected to treat. So the system is pretty robust. Average load is 50% of the design. This is a question of what design was selected at the beginning, but most of the time we're about 50% with peaks, depending of the need on site. Now, as I told at the beginning, this is a mine in northern Quebec, cold temperature. So it's very important when you're operating in mining operation, when there's cold water, all the process will react. This is a biological treatment. We are expecting to meet some resistance at lower temperature. During the first winter, the water temperature was limited at 8 degrees C. Reason why the water quality was not stable when we tried to go lower than 8 degrees C. The biomass was not mature. So the heating was used to make sure that we kept to the 8 degrees C as designed. Subsequent winter, which is last year and this year, this is interesting because the water temperature was decreased down to 3 degrees C. And this is not a reason, we did not treat at 3 degrees C because this is the limitation of the process. We stopped at 3 degrees C because we were scared to freeze the line. So there's a very limited heating required for not the last winter, but the last 2 winters. And it's mostly due to make sure there's no freezing because there is no heat tracing on the piping of the MBBR. Then nitrogen species. We'll look a little bit about the nitrogen species. So look at the little red dots here. These are the nitrite concentration. You can see at the beginning of the treatment, the nitrite is high, but it goes down all the way down when the startup is completed. This is the time the biomass is acclimating itself and all the species are in place within the carriers and the right reactors. Because at first there's cyanide removed in the first, ammonia removed in the first reactor, and you need the system needs to be balanced. So this is a transition period where the nitrite was slightly higher. But you can see that since 3 months after the startup, it's very low and it stays low. Nitrogen species, you can see blue dots are ammonia at the effluent. Water is non-toxic since the startup, where they started to test it in November, and it's non-toxic since the beginning, which is very important, at least for the client. And while there are still variation of ammonia concentration over time, there are some peaks that can be seen. The water quality is always improved. The peaks are not as long. The water quality reestablishes itself quite fast. And each of these peaks do have a reason. For example, the last peak was due to an historic rainfall on site. They had a lot of water stored in a pond and they needed to get rid of the water. They sent it to the MBBR. We suspected the water composition was slightly different than the one coming right from the mill. And the MBBR took a little bit of time just to adjust to the different fractions of cyanide species and ammonia. But overall, the process was pretty robust and goes back down with good water quality. So now, takes away. Toxicity is not something simple. You need to correctly identify what causes the toxicity and how to treat it efficiently, because it's not always the same and it doesn't react the same either. Second, don't go too fast if you're not sure. If you're not sure what your toxicity source is or how it can be efficiently treated, take the time to do some lab work and even go with piloting, because you can be sure while doing these to have a correct design to make sure that everything works good before installation on site. And that way you can really work together, a consultant and the client and Veolia, and make sure that you really have a complete solution that will really get rid of the toxicity. And third, but not the least, biological systems can work in mining operation, even in cold water operation down to 3 degrees Celsius. They are working really great, and like good wine, they improve with time. As you can see in the graph, the water quality keeps improving over time. So biological treatment really do work in mining operation, even in remote location, cold water, it works. And just the cherry on a Sunday, we still are in communication with people from the mine. And until recently, there was still no mortality ever seen on the final effluent, which is really an excellent thing, and the client is very happy. So thanks you all for your attention.
Okay, thank you very much, Miriam, for that presentation. I just want to remind everyone that we do have an option to ask questions. We did have a few that have come in throughout the presentation, but I just wanted to remind you as well. You can ask your questions via the questions panel over to the right-hand side in your panel. And with that, we will get our question and answer session started. Miriam, one of the questions that came in is regarding the pilot, what was the source of the toxic shock?
We believe it was some maintenance soap, or they did some maintenance on the side and there was a spill of soap, or like really to do some cleaning products that just spill on the floor, was washed down to the drain, and it goes to the pilot eventually.
Great, thank you. I've got a couple questions actually regarding temperature. First one is, I guess, what is the best average temperature for the MBBR application? And then just to follow with that as well, what is, I guess, what's the limit of temperature limit for MBBR?
Well, we'll start with the first part of the question. What's the optimal temperature for the MBBR? There's no optimal temperature. It's mostly, we design based on the temperature you want to have on your MBBR. If you go at higher temperature, the kinetics are going to be faster. But if we know from the start that the MBBR will be operating at 3 degrees Celsius, the system at 3 degrees Celsius will be very efficient and will treat all you need to treat. And now what's the limitation, the lowest temperature? We tested as low as 3 degrees Celsius in that case study, and we were limited to make sure there's no freezing. In some municipal application, they go lower than 1 degree Celsius. Well, the limitation is you don't want MBBR to freeze. You don't want the water to freeze. But is there a limitation? We haven't found one yet. This is the real answer. We have not found any limitation yet.
Okay, just to follow up on that, talking a little bit about temperature as well. There's a question in here. Do you have any references of upscale plants operating between, say, 1 to 3 degrees Celsius?
Well, the case study just presented at some point at 2 degrees Celsius. This is a very low temperature. Lower temperature, the problem is really that you don't want to have any water freezing in your piping. So it wasn't tested yet because you need to prevent freezing in. It's just a mechanical protection from there. So this one is running at 2.5, but lower than that, it's just a question of preventing mechanical freezing.
Okay, another question that came in is what flow rates were treated, and then also what's the residence time?
I was not the principal engineer on that one, so if Mark is there, can you jump in and give the details of the flows for this application?
The system is designed for, I do apologize for Americans, it's designed for 26,000 cubic meter per day, which doing a quick math is probably a bit less than 5,000 USGPM. Mind you, that's the hydraulic capacity. The system is normally operating at half to 2/3 of that value. Residence time in the reactors is on the order of 30 minutes in the first and a little bit over an hour into the second reactor, but obviously that depends on the flow rate, and so low flow rate will be higher, high flow rate it will be lower.
Great, thank you, Mark. Another question is it possible to operate this process, say, on and off, for example, only in the summer or during a certain period of time, or does it need to be continuous?
There are possibilities to work around. We tried with the client to work around to do seasonal operation, but you have to keep in mind that you either need to send a little side stream to make sure you keep your biological and your biology active, or you will need a startup time. So you have to get some time before you need to actually treat the load to reseed your system. So it's not impossible, but it needs to be discussed between Veolia and the client to make sure that we really understand why it needs to be worked seasonably and what could be applicable in that particular case.
Great. Another question was, processed water was mentioned to be high in chloride. How did chloride concentrations impact the bacteria?
It's not saline water. So it has no impact on the biology at the level seen there. If the level is higher, it might be a different type of biology. It will react differently, but it doesn't mean it's not going to work. It's going to be different. You will manage your commissioning differently.
If I may, Miriam, the impact was not as much on the biology, it was on the material of the construction. The chloride numbers are in 2 to 3, 4,000, 4 is high, but say 2 to 3,000 ppm. That was a challenge for material construction selection, but the bacteria themselves don't seem to be affected.
Great. Another question is, how can this process cope with various climate changes?
Well, usually climate changes are, the variation are not sudden. These are coming slowly. In the case of, let's say, heavy rainfall, the hydraulic can be pretty robust, and loading you just have to manage your system to be able that the system won't see it one shot. You just need to be like I don't know how to say it correctly. It needs to be progressive, but it can withstand fluctuation. There's no problem. It can vary in temperature, in flows, in loading, but it just needs to be a little bit progressive. So it's just a question of how you manage your system.
Okay, another one that we've got that came in is, are there other metals that inhibit biological activity apart from copper?
Copper is the main inhibitor. You can have some inhibition by cobalt, nickel, arsenic, but concentrations are so high that you will rarely have these high concentrations. So this is really a problem. Copper is the main inhibitor seen for biological treatment.
Okay, a question regarding thiocyanate. What was the cyanide? I apologize for that. What was the thiocyanate concentration in the effluent?
I believe it was around 300. Am I correct?
In the effluent or the influent?
In the effluent, please.
Oh, it's below
Oh,
1. It's undetectable. Basically, we're below detection limit.
Sorry, I understand on the influence, but no, in effluent, there's nothing left there.
Another question that we've got, how the nitrogen load, ammonia concentration, and nitrite concentration monitored or analyzed during the process. Was it done on a daily basis, or what was the testing of that?
They're doing laboratory testing twice per day, once per shift, and there's an analyzer, online analyzer that was installed. I don't think they're using it anymore because it's easier going with the lab testing twice per day, and the variation are not that big, so it's manageable, but there's a possibility to put an analyzer to follow it online.
A question regarding BOD. What was the BOD level in the effluent?
Low. It's a low BOD.
Okay. Bear with me. I think we've got time for probably one last question here. And I do apologize if we did not get to all of your questions. We had quite a few that came in, so I do apologize if we did not get to those. We will follow back up with you regarding that specifically. So one last question in here. Is there enough alkalinity produced in the R1 to avoid alkali dosage during the nitrification? And then how much alkali do you save with this bicarbonate production?
This is a good question. There's still a need to dose alkali because nitrification requires a lot, and there's not so much formed during the transformation of cyanide species to ammonia, but I do not think we made the calculation to know if there's any alkali saving. Mark?
Sorry, I unmuted myself. No, we did not make the calculation. This is a mine ore coming from an area where there's very little alkalinity in the rock. So the ore coming in actually has very, very low alkalinity. On their 50, 70 milligram per liter CaCO3. So it's way insufficient to balance the production of the nitric acid. So no, it's simply in this specific case it doesn't work. That doesn't mean that it will be the same in every situation. If you have a stream that contains a lot of alkalinity, little ammonia, you might actually be able to keep the pH constant without having to add alkali, but not in this instance. Not sure if I answered the question.
Great. Thank you, Mark. And I do want to thank our panelists today, Miriam, for that very informative presentation on toxicity for gold mine effluent. Just a quick reminder that we do ask that you fill out a brief survey, 20 to 30 seconds at the conclusion of today's webinar. Those that do fill that out will be entered to win a $25 Amazon gift card. And one other thing is if you enjoyed today's webinar, we do invite you to take a look at our upcoming series as well. All of the webinars are posted on www.veoliawatertech.com, as well as the on-demand webinars that we have conducted in the past are all listed there as well. So we do thank you for your time today, and we hope you enjoyed today's presentation. Thank you.